I'll let you the stage because we're already bit out of time. Thanks for your attention. Yes.
Thank you very much, Stefano, for your kind invitation and presentation. And
if you want.
yeah, okay. Today we'll have some lecture on different methods for characterization of material. Can you hear me? Yes. Okay. And please not hesitate to contact me for any queries and anything about the presentation. So the topics today are related to the different type of characterization techniques. One of the first is electron microscopy, and we have in our department in Bologna different type of instrumentation for electron microscopy. We show you exactly the difference and how they are used for. But also we have other type of microscopy, scanning probes, and also X-ray diffraction for characterization of minerals, materials, of all material which is in a crystalline state. I should have 4 hours, but I promise every hour I will take 5 minutes break. Okay, so we'll start with electron microscopy, some theory, instrumentation, and examples. I think that from practical examples, the teaching of one lesson will be much more clear if after the theory and the technology, you show how you can do with practical examples. Okay, we have this dark bar, but I think it could be the same. So these are the facilities of. Okay. These are the microscopy facilities we have at the BGEA. BGEA is our department, biological, geological, and environmental department. And in Bologna, we have this type of facilities for electron microscopy. I will show you in detail. We have a field emission, FEG stands for field emission gun, environmental scanning electron microscope, which can work also in transmission. So it's FEG, ESM, STEM. STEM means for scanning transmission electron microscope. You have the electrons which are transmitted through the specimen, but also with the scanning over the surface. Then we have two types of classical transmission electron microscopes, the image in here. We have also classical SEM, and also a scanning probe, which always use the scanning to understand the material, but does not use electrons in the classical state of meaning for electron microscopy. It's a classical atomic force microscope. And also a confocal light scanning electron microscope in the top left. So we have all this huge amount of different instrumentation, not just because they want to collect all type of microscopes, but because every type of instruments has its own specific application. And what I hope today to pass as an information is for specific experiment we have to do, for specific analysis you have to do, you can choose a specific instrument to do that. So we start with the scanning electron microscope. This is the instruments. You see there is a big chamber here, huge chamber. We can allocate object with 10 centimeter in size, in average. And around this big chamber, there are a lot of different type of detectors. And you see beneath the chamber, you have this huge amount of engineering tables and parts, the pumping systems, and a lot of other things. So the main part of the instruments is this, and you will control the instrumentation by using this keyboard. Here on the right, I just put the classical part of the instrumentation. You can have here a field emission source. So the electrons are produced by a field emission gun. And if you use a field emission gun instead of a classical thermoionic one, you can have much more electron per unit of space area. So the density of electrons is much, much higher. And what does it mean? It means that if you have a small probe, and this small probe should hit and some way analyze the material on the surface, you have a huge amount of electron in your small probe. So you can have a very, very high signals which comes out only because you have this type of source. Because from the optical point of view, if you have a source here, you produce some sort of pinpoint of electron, and all the electron lengths will produce the same point on the top of your surface. So if you have huge amount of electrons, you can have huge amount of signals. The system is also, you see here, this E is also an environmental SCL. This means that if you have an hydrated sample, if you have a wet sample, if you have a sample in which you want to leave the biological, especially biological condition, you don't need to evacuate the chamber. Because if you evacuate the chamber, you remove gas from the chamber and you remove water, for example, for biological material. And your biological material change in morphology and change in the structure because you remove water during the observation. This device, this instrument was specifically designed to work with high pressure, only at the specimen surface. So you don't need to have high pressure along all the column. You need to have high pressure only close to your specimen. So the idea is to build a system in which you can produce electrons in high vacuum. You can accelerate electrons in high vacuum, and only very, very close to the specimen surface, you can have high pressure. So the main paths of the electrons are traveled in high vacuum condition. And only the last part, very thin last part, the electrons pass through an atmosphere and then hits the sample. In this case, the scattering of electrons with the atmosphere is reduced because you have atmosphere only very, very thin layer above the surface. And we have two advantages. You don't have scattering of electrons, broadening of electrons due to atmosphere, and you can maintain your biological sample in the biological state with water. So this is the idea of this system. Yes. Cells, tissues, whatever, but also someone is interested in crystallization of salts in water condition. You can plan to do experiments in which you can remove water and add water on your specimen. So you can see how the crystals grow and how the crystal dissolve. You can change the temperature. But for the biological means, you can observe the biological tissue without any alteration. So this is the usefulness for this. But during the lecture, you will see many other applications. But the most important that the biological tissue can be observed without any preparation and without any modification during the observation. If you have a question, please ask it. Don't be shy. The other thing is that, yes, please.
Is it possible to visualize proteins?
Yes, yes.
Can you locate them?
You can locate proteins inside your specific biological object. What are the size of the protein? I assume it's quite a small size. So the resolution of the instruments is about 1 nanometer. So if your object is in the size of nanometer or bigger, it's possible to see the morphology and to localize respect to the other part of. I will show you also another effect that will be very, very useful for the biological material. With this type of instruments, with high pressure, just close to the specimen surface, you don't need to cover your material with a conductive layer. If some of you already work with a classical scanning electron microscope, probably remember that many technicians, many specimen preparation methods require to cover your sample with gold or carbon to create a conductive layer. Why? Because remember, you are using electrons to observe. If you use electrons and your material is an insulating material, and most of the biological material will be insulating, the electron produced by the source remain localized where they hit in the specimen. And since the material is insulating, the electrons does not move. The electron produced by the source hits the surface and does not move. And you create a charge, localized charge in the, and this can create artifacts in the observation. So usually, in most of the classical SEM, you need to cover your surface with a conductive layer. Usually is gold, but most often could be also carbon. But you need to cover all the insulating material in a classical SEM to remove the charge. During the observation, you accumulate charge. You don't need the charge. The charge creates damage. You need to cover with a conductive layer. If you cover with gold, you can have problems with the microanalysis. When you want to detect elements, you have the gold on the top. We can create a background and can reduce the possibility to have information from the chemical point of view. If you coat with carbon, you need to create a thin layer of amorphous carbon on the top, and this layer is conductive, but can prevent the observation of tiny details if you need to have a nanometer scale resolution. So in classical SEM, you must cover the sample. In the environmental, I will show, you don't need to cover. So you have two advantages. The first, you can observe in high pressure, water condition. And the second one, you don't need to cover. So when I explain, I can take whatever type of biological sample you put in the chamber, we can observe without any preparation and without any modification in the structure. So the usefulness of these methods is much more felt in biology than in material science. You can work also in transmission. We have a special device. So if you have, if you want to increase the resolution, you can work also in transmission. And here there is the list of the classical signals which are used to create information from the topography. Secondary, electrons. Why they are called secondary? Because the primary electrons are the electrons which are produced by the source. So the source produces electrons. This is primary electrons. After the interaction with the specimen, you have other electrons. I cannot call the other electrons primary. I have to call other electrons secondary electrons, electrons produced by the primary beam. And these secondary electrons can give you information about the topography down to the nanometer scale. But also you have other type of electrons. You see here, backscattered electrons. Backscattered electrons, the name backscattered, are the primary electrons which are reflected back. As in a collision, you have small ping pong balls or tennis ball, you hit with the balls the wall and the balls came back. So they are scattered back. In this case, you can detect the primary electrons which are scattered back. These are primary backscattered electrons. So the secondary are electrons which come from the surface. The backscattered are the electrons which come from the source and are reflected back. Why do we use these two different types of electrons? Because they are sensitive of different type of information. With the secondary one, you can detect the morphology. With the backscattered, you can detect the chemistry, variation in chemistry. If you have a small atomic number element, the probability to reflect electrons is small. If you have high atomic number element, the probability to have back reflection is high. So if you use secondary for morphology, in parallel, you can use backscattered electron to have chemical information from the surface. High or low atomic number. Just an information.
When you get the chemistry, okay, you have the data about the elements that are present in the samples, but you also, if you do a map, you have a coordinate, geographic coordinate of the point where the elements were present, right?
Yeah. So
the output is the distribution of the elements in a given surface area, okay, and also the position of each element. So you have two kinds of information: spatial. And
well, with secondary electrons, you also only have the morphology. With the backscatter electron, you have a map of variation of the atomic number. With the third signal, X-ray microanalysis, you have the element map.
And the map gives you the amount, I mean the quantitative, but also the geographic position.
Yeah. How much element is in that point and how is distributed on the morphology of your cell.
So the raw data gives you also the code. Yeah. The geographic code.
If you set up the system to have a map, it's called X-ray map. This means that point by point, you have the map, the coordinates of the chemical element. But this is a dashboard here, no? Okay. We have to keep it in mind that the resolution, the spatial resolution is very different depending on the signal. So don't think that every signal has the same high resolution. I mean spatial resolution. I will show what I mean. If you use secondary electrons, you have a very, very spatial resolution. You can detect under nanometer size object. With the backscattered electrons, you have a resolution of about 10 nanometers. With X-ray microanalysis, you have a resolution of a fraction of a micron. So the signal are different, but also the resolution are different. Please keep in mind this. If you want to increase the resolution with the chemistry, you need to prepare the sample in a different way. But we show you how, because Okay, this is just the first slide.
Yes.
Okay, because when you have electrons which comes through the specimen, you have ionization inside, and the region in which ionization comes from is much higher than the region from which the secondary electrons come from. So the resolution, the minimum volume from which comes the information is completely different. So you can get different information, but remember, the spatial resolution could be different. But I will show you. Then we have X-ray microanalysis for chemical information. So the same electrons produce ionization, and after the ionization, you have the production of X-rays. These X-rays are the fingerprint of the chemical elements. So if you detect these X-rays, you have a map of the elements which are inside the specimen. Then you can also have cathodoluminescence. You can produce light after the interaction. And if you produce light, you can map the lights where it come from after the interaction. You can have electron bescattered diffraction, EBSD. So your electrons hit the specimen, but they are reflected back not by the atomic number of the element, but they are reflected back by a diffraction mechanism like Bragg diffraction. Depends on the plane of your crystalline material. You can heat, you can cool the stage, and you can change the pressure. All these things you can you work with inside this chamber. So think at this instrument not only as a just instrument, as many other. You push the button, you get the information. With this system, you can plan, you can project, you can create your experiments inside. So this was the idea I want to pass you. It's like a lab in which you can create your experiments down to the nanoscale, because all these facilities are available. You want to see how it behaves in temperature, you can plan a project in which you heat your specimen and see how it changes in temperature. You want to see how it behaves in cooling, you can plan an experiment in which you can cool down your material. You want to observe the chemistry at the nanoscale, you can try to see the chemistry at the nanoscale. You want to see the optical behavior, whatever. You can plan. This chamber is a lab in which you can create your experiment, not just observation. You can do just observation, but it's more. You can plan whatever. So since it's an environmental instrument, you can change all these variables: pressure, temperature, gas type. You can also have, I forgot to mention before, also mechanical test. You can, we have a tensile and compressive stage. You want to see how your cell or your tissue behave after applying a tension, a mechanical tension. You can apply a mechanical tension or a compression and see how your tissue behave using this mechanical part. You want to apply an electric field to your biological materials. You want to stimulate your cells with an electrical signal. You can do. You have your tissue, you can apply a voltage and see how the cell behave. You can apply a voltage with also an applied mechanical test to see the behavior of your tissue in physical condition and also in temperature. I just summarized the three vacuum modes of the system. You can work just in the classical SEM in high vacuum. Usually it's about 10 to minus 6 torr. You can work in low vacuum, 1.5 torr. And you can work with environmental SEM up to 30 torr as a function of type of gas, in nitrogen, in water pressure, water molecule pressure, water vapor. Most commonly, we use air or water vapor. But you can plan whatever type of experiments using the gas you need. And in situ studies in temperature, we have a Peltier and the heating stage, which can work to minus 25 degrees Celsius up to 1400 degrees Celsius. So you can cool and heat your material in this range. The systems, this is an image of what you have inside the chamber, what you have here. This steel base is a base for, you see, these holes for allowing to set up many types of samples. You can fix 20 different types of samples. You have a big chamber. Also, you can fix a huge sample if you have specific requirements. For example, in cultural heritage, you know, people which work with in museums and arts, they are not very keen to take part of the painting or part of the arts, because they don't want to damage. But you can put directly inside the chamber all the part in the limitation of the size of the chamber without taking any part of your material. So if you have object this size, they can enter without taking any part from the object. Just for curiosity, this type of instruments was built also for specific requirements for the British Museum or very important museum in the world. But the chamber was built as the size of 2 meters to allow paintings to enter without any damage and without any preparation. But the physics of the system is the same. Only the chamber is bigger. So this is the typical working condition, current of from picoampere to 200 of nanoamps with accelerating voltage from the range of kilovolts, but down to some volts. And we can also decelerate the electrons down to few electron volts inside the chamber. So if we have very fast electron, we can decelerate the electrons and allow the electron to hit very gently the surface. And the magnification range of the instruments comes from 6 to about 25 millions of magnification. The goniometer is eccentric, which means that you know what is eccentric. Eccentric means that you can fix your sample, and usually when you rotate, because you have a tilt, the sample rotates with the tilt, and you lose the sample, because if the electron hits here and you rotate, you move your object with respect to the electron. But we have eccentric goniometer, so means that we can rotate the sample with an axis, ideal axis inside the sample. So the sample rotates in this way without moving. This is very important if you want to see morphological aspects of your material and you want to tilt your sample without losing your sample in the field of view during the observation. You can do this with this goniometer. And the multi-sample holder, you can observe up to 20 different type of objects. So this is the back of the instrumentation. You can see the different type of detector. I just show you by name. So the X-ray detector, the secondary electrons, the backscatter electron detector. So it's like a star. Every detector has a specific position around the instrument. And also the heating stage, the stage to cool down your specimen. Catluminescence detector is in the other part. And this is the STEM detector. So different type detector are all arranged around the chamber. We have also a plasma cleaner to polish some metal or ceramic material. We can create a small plasma. Plasma is ions, huge amount of ions. These ions clean the surface. Then you remove the plasma and you have a clean surface. This is used for metals and ceramics. Okay, let's go in much more detail about what happens when electrons interact with the matter and how we can get the information from the material. So before going to detail, I just like to show you some examples. In the 1889, using wrought iron, one of the tallest tower was Tower Eiffel, and with wrought iron, remember the year 1889. The yield stress, so the maximum stress that the iron or the material at the moment in that year could be thought to be used to create a tower, has a stress of about 200 megapascal. So if you apply a stress higher, the material deforms. If you want to build a tower, to be sure that the weight of the tower cannot deform the material. So at that time, using wrought iron, the maximum height was about 300 meters with this shape in the total. This is related to how the material behaves as a function of mechanical properties, like, for example, tension or compression. Now, Sky Tree, Tokyo, it's about 600 meters, always metal. This is wrought iron, and this is steel, high-strength steel. You see, changing the always metal. Both are metals. Both are metals made of iron, because this is steel and this is wrought iron. But understanding how atoms are arranged in the crystal structure allows you to build completely different and sustaining things. Always lattice of iron, but understanding how the crystal is made, now you can sustain 600 meters instead of 300 meters. Just understanding how the crystal is made. At the same time, this is glutamate dihydrogenate. This is a high-resolution cryo-electron microscopy image on the right. And this was an image taken many, many years ago in which you don't have resolution. You see the form, the shape. You have the similar shape, but with increasing resolution in the detection technique, you can detect finer details of these biomolecules. With the resolution, you can detect the atom position. With very high resolution, you can detect the atom position down to 1 angstrom resolution. You can see atoms, how are they arranged with this type of specific preparation. If you don't have resolution, you can have the shape of your object, like the left part of your molecule, but you don't see the single atoms where they are. So understanding how the crystal is made is fundamental in different types of disciplines, from the engineering point of view and from the biological point of view. This is a rush to the high spatial resolution. We are looking for instrumentation technology to see where the atoms are and how the atoms are. And when I say atoms, I think to this part of your molecule. We can detect where the atoms are down to 1.8 resolution. And for the engineering point of view, if we understand how the atoms are in the crystal, we can create object or towers tall like this. Just an example I show you. Do you know what is wrought iron? If you have a perfect crystal, and you apply a stress force, atoms, it's a perfect crystal. Atoms tend to move along planes. And if the crystal is perfect, it's easy to move planes. They didn't know at the end of the 18th century. But if you hammer your iron, hammering, routing, you create defects inside this location. And these defects inside prevent planes to move. So wrought iron, hammered iron, is much more resistant than pure crystalline iron. So the role of how the atoms are arranged is important for the properties. If you have a perfect crystal, can be used for specific application. If you have crystal with defects, you can be used for other. I don't like the term defects, but if you look in a material science book, they call defects the material with a lot of defects. They are not defects, they are beauty, because controlling these objects, we can increase, we can create our technology for our specific need. Just understand how the atoms are. What do you think? Can continue or? Oh, okay. So okay. This is another example of what I mean for resolution and dynamic electron. In the left, I just surrounded with red is just one bacteria. Don't ask me which kind of bacteria, it's just an example. And this is just an image, scanning electron microscope image, SEM, in which you can measure and see the morphology of your material. This is classical SEM, not an environmental one. The same bacteria was extracted and grafted and placed on a scanning probe microscope. It's not an electron microscope. It does not use electrons to see the object. It uses a very, very gentle probe that we show you later, just to show you what we can do. And in this type of microscope, you can work in liquid and very high pressure. So you can see how your bacterium behave. And colleagues from the pharmaceutical department would like to try if this antibiotic can work or not to this specific bacterium. So they applied the antibiotic after 0 seconds, 10 minutes, 20 minutes, 30 minutes. And this red circle here is the perimeter of your bacteria. You cannot see anymore the bacteria because you are using this instrument. And this instrument is very sensitive to vibration. So the idea to plan these experiments, okay, I want to fix one bacterium. I'm not interested in the shape. I want to see only if vibrates or not. If the surface of the bacteria vibrates or not. And if apply an antibiotic, how do the bacteria behave as a function of the vibration? So you see, this is the vibration, the interaction of the membrane with the light, which vibrates, and the system detects the vibration. If you apply the antibiotic, after 30 minutes, you have completely removed any vibration from the surface. So this was just an example of how you can use microscopy to verify the functionality of an antibiotic. Just planning a specific experiment. Okay, some words to be noted, something to be remembered. These are just a slide on recognition was given to people who developed microscopy things. So the Nobel Prize in Chemistry 2017 for the cryo-electron microscopy was capable to have angstrom size resolution. In 2014, the fluorescence microscopy gave the possibility to this researcher to get the prize because with optics, with the photon optics, you have a resolution of nanometer size. And many, many years back, Professor Ernst Ruska in Germany in '86 got the prize for the development of the first electron microscope. But the prize was shared with Binning and Rohr. With the same time, they developed the scanning tunnel microscope, the atomic force microscope. So the first recognition on microscopy was in 1986. Both electrons and atomic force. So these are the guys from the classroom at the Cavendish in the 1914. And if you can recognize some of this old professor, this is J.J. Thomson, the professor who discovered the electron. And this is Rhys Wilson, the professor who developed the cloud chamber. These are instruments used in nuclear physics. So you have supersaturated water vapor on the top of a chamber. If a particle passes over the saturated gas, create condensation. And if you measure the condensation, the path, you can measure the path of your particle. This is William Aston who discovered the isotopes. This is the young, very young William Lawrence Bragg for X-ray diffraction. And this guy is Paget Thompson for the electron wave properties. So why I use this slide? Because in this year, the waves are coming. About 100 years ago, the waves are coming. We are talking of electrons, we are talking of particles, we are dealing with particles, but the waves are coming. So in the same time in which Bragg use waves, use X-ray, which are waves, to detect the crystal position of atoms. At the same time, some people understood that even very, very small particles could have a wavelength. And this is the famous formula in which you have a correlation between P, which is the momentum, the mass per velocity, mv. It's a mechanical quantity, mass per velocity, which is, you see, in the formula, equalized to a function in which you have a lambda, a wave function. So summarizing means that every particles can have a wavelength. And if every particle can have a wavelength, you can create optics with particles, because particles are waves. And they understood this at the end, in the beginning of the 19th century. So we can use the same optics we know for microscopy to deal with electrons, because electrons can be understood, can be behaved like particles. So the diffraction limit is a limit related to the wavelength, in which we have the fixation of the smallest object we can observe. This is a diffraction limit, a typical limit in optics. And the spatial resolution of every type of microscope, optical, electron, whatever, every type of microscope, the spatial resolution is limited by the diffraction limit. And the formula which gives you what is the smallest object I can see with this type of microscope, the diffraction limit tells you that the small object, which is the spatial resolution, is d, is equal to lambda half. Half of the lambda is the spatial resolution. If you have an optical microscope, you are using light, you are using optics. What is the spatial resolution? What is the smallest object you can see? Half of the lambda you are using. You are working with the lambda, the visible lambda, 3,000, 4,000 angstrom. The resolution is half of this lambda. This means that object smallest to that cannot be seen. You can put many magnification to the system. You only enlarge a confused object. You can pass the resolution. Here on the light, I put this limit, you see, light microscope, human eye, electron microscope. I put just this limit related to the diffraction limit, 200 nanometer. Object smallest than 200 nanometer cannot be seen with classical light. And at the same time, I put on the slide object you are interested in, virus, small molecules, ribosomes, atoms. All these objects are below the diffraction limit if you use light. You can magnify whatever you want. You only increase a confused object. If you want to see the details, if you want to increase the resolution, you need to change the wavelength. Okay? So the human eye has this limit, more or less 100 microns. The best eyes can do 50 microns related to the diffraction limit. But in our case, if you want to see atoms, molecules, you need to pass the light microscopy. But in the slide before, I told you that the particles can behave like wavelengths. So we can create a microscope with waves using particles instead of photons. And in this case, you see in the back of the slide here, with the electron microscope, using electrons, and this is the reason why I told you at the beginning, with electrons, you have a very small wavelength. And since the wavelength is very small, the diffraction limit is close to the size of the object you want to observe. You want to see to observe. And now with an electron microscope, with a modern electron microscope, you can see directly atoms. This means the wavelength you are using in your electron microscope is smallest than the atom. So you don't have to think about the diffraction limit because the wavelength is much more smaller than the object. But you need to create this type of instrument. And this is the reason for electron microscopy. The same thing I just told you before, with X-rays, you can have this type of resolution. Now with electrons, we can have this type of resolution. So we can resolve atoms in the solid. Just to be complete, maybe some, can we use other small object to create magnification, to create images? Yes, you can use helium atoms. There are microscopes which work with helium atoms. With helium atoms, the wavelength is very small. You can have a resolution down to 1 angstrom. Or neutrons. You can use neutrons to create image, thermal neutrons. You have 2 angstrom resolution. But this is just an information in physics. I mean, since you know the diffraction limits, you can think to a particle, you associate to the particle the wavelengths, and you can create whatever, but it's not very useful. This was done just to show that the working principle was right. Look at here, 1930, 1945. If you have a small particle, you can create a microscope. Now, we have very easily electrons, and electron microscopy is very easy and diffused. So you can have very small particles, very small wavelengths, very easily today. This is just the story. So from the Bragg law, we have all this type of development instrumentation. So from the principle of the diffraction limit from Bragg, we have all these type of different instrumentation. Today, I will focus mainly on electron microscopy, but to be clear, also to think other experiments or to think other in biology, you can have other facilities for other type. For example, you can use X-rays for diffraction in crystallography. If you have crystal, if you have hydroxyapatite, crystalline apatite, or crystalline proteins, or crystalline biological object, you can use X-rays easily. You can do neutron diffraction if you want to observe a crystal which interacts with X-rays and you want to avoid this such an interaction or interaction with electrons, you can use neutrons for diffraction. And well, obviously, you can use electrons, the subject of the lecture today, in scanning and transmission electron microscopy. You can use electrons. And you can use also electrons with very, very small energy to understand the fine structure of solids, how the electron behave in bands in solids. At the same time, a lot of technology have developed from the spectrometers, source camera, Bragg mirror, electron microscopy, instrumentation, and you see the computing power in the last year increased. So you can do also simulation at the same time. So you can write the physics of the system. You ask the computer how should be the information. You can simulate. You can observe and you can simulate. Oh, with X-rays, you can reconstruct 3D with X-rays. Yeah, well, you mean the difference? Why using?
So that you really get three-dimensional image.
Well, I think with the electrons, using electron microscopy, you can detect three-dimensional information.
Basically only the surface.
I wish you can have information also from inside. But when you use electrons, usually if you have small objects, if you have bigger objects, you can use X-ray to do crystallography. X-ray interacts less strongly with matter respect to electrons, and you can have a 3D reconstruction of object using X-ray. In X-ray crystallography, we can reconstruct the crystal, and the crystal could be of the size of few millimeters. This is not possible with electrons, because electron would be absorbed in 1 millimeter crystal. But if you have 1 nanometer, 2 nanometer, 10 nanometer object, you can do with electrons because they pass. So depending on the experiments you are looking for, you can choose the different type of instrumentation. I think we can have 5 minutes break.
You look at me, my eyes. You are more like a studies. Very, very interesting, bellissimo.
Penso di saltarne alcune perché è meglio andare alle applicazioni.
poi rimettiamo la 1.
Appena aprila.
Sì, tolgo questo e le metto, se è più comodo, il laser, si vede meglio nella freccia.
Per tornare indietro così, vero? Tornare indietro
Con le fette?
no, con le 3.
Ok, qua.
Ok.
Sì. Qui, ok.
E lui per questa qui.
Ecco, esatto.
Perfetto, questo.
Ok. E appare la barra sotto, devi cliccare una volta la barra e una volta la presentazione per togliere.
Okay, we can continue the lecture on microscopy. So I said before, from the 19th century, we have what I call the microscopy Big Bang. So a lot of different type of microscopy technique have been developed since these years. And I try to summarize all the different types in this slide. But some of these I will underline during the lecture. Why? For a didactical point of view, I don't want to that anybody should have any confusion about the different methods in microscopy. So we are dealing in this particular moment, this lecture, with electrons and electron microscopy. And this is what's been developed using electron in these years. And today I will focus mostly on environmental, but there are many other techniques with microscopy with electrons. Scanning transmission, conventional transmission, high resolution transmission. We will find a lot of different type of electron microscope techniques if you look around in every labs around the world. And every different type of instruments was built as a function of what you need for. If you need high resolution for molecular resolution or atomic resolution, usually you should have high resolution DEM to do that, even with biological material. But the preparation is completely different. If you want to observe the surface or the chemistry of a bulk material, you can use a scanning electron microscope or an environmental one if you want to keep the status of your material as much as possible, as close as it should be. But this slide shows you other microscopies that have been developed in these years and can create some confusion if I'm not clear at the beginning. Most widely used instrumentation in microscopy are called SPM. I know this whole acronym can create confusion because S stands for scanning again, and P stands for probe, and M stands for microscopy. So SPM is again a scanning probe microscope or scanning probe microscopy. So how I want to be clear, what is scanning probe microscopy? Why I use again scanning, I use again probe, I use again microscopy? And I try to be clear using this slide. So when you have and when you use electrons and you have an electron microscope, the probe are the electrons. The probe, the source, the physical object I use to get information from the interaction with the specimen are electrons. And usually in the acronym of the technique, you have the letter E, like environmental scanning electron microscope, scanning transmission electron microscope, conventional transmission electron, high resolution transmission electron. So usually when you have an electron microscope, you have the letter E, which stands for electron. Even if you have scanning, if you have a probe, if it's a microscope, whatever, you're using electron. So all these on the left are called electron microscopes, which work with different engineering techniques, but they all use electrons. So what are these? And you may be found in everyday labs. We have also in Bologna. What are these SPM? Scanning, probe, microscope. Are a different type of instrumentation. They don't use electron as the electron microscope. But you have a probe. I will show you next lecture with what is a probe in this case of SPM. It's not completely different from the electron microscopes. You have a probe, and this probe is not fixed, makes a scan. So scan moves, scan, it's a probe, scan, probe, microscopy. I want to be clear at the beginning. So this scanning probe microscopy, maybe you know atomic force microscopy, maybe you know scanning tunneling microscopy, are a different type of microscopy which use scanning as an engineering method to acquire information from the surface. They use a probe. They are not electrons, are different type of probes, and the names are scanning probe microscopy. I will show you the difference to be clear just at the beginning. When you use electron, you are electron microscopy users. You use electron to create the information. The electrons can be scanned, so it's a scanning. The electron can be transmitted, so in transmission. The electron can be reflected, so different type of electron microscopes. So all these in these slides are microscopes. Instrumentation, we try to enlarge an information. But remember, always be connected to the resolution. The green part, I'll escape this, is optical. You know, the optical microscopy. It's a microscopy, classical microscopy. All of you know, maybe have all used an optical microscope. Is a microscopy, but with a very, very low resolution, not very high resolution, just useful for micro, half a micron size object. And I don't want to say that the electrons are better than the optical or the SPM. No, all methods are beautiful. All. They have developed for the specific. If you want an information for a large object and you don't need the resolution, you should use an optical one. Large samples, large information, average information. It's a very useful technique to start with. If you want to localize one cell, if you want to localize one bacterium, you can use the optical one, and then you have localized your object. Then the object you can fix on a holder, on stub, support, and take your object and go inside the electron microscope. We do this every day. First, we observe by naked eye our rock, our tissue, our whatever, our clothes. Then we decide whether the object to be studied. And then we observe with an optical microscope the feature we are looking for. Soon after we detected the feature with an optical, we select the object, we extract the object, and we put the object in the other type of microscope, depending what you are looking for. At the same time, I introduced diffraction. Why do I have introduced diffraction? For two reasons. The first one is that the physics which prevent you in observing small object is related to the diffraction principle. whatever wavelength you have, you cannot see an object which has a size less than the wavelength you are using as a general rule, half of the wavelength. So if your wavelength is micron, you cannot see nanoscale objects, like in optical microscopy. So if I introduce diffraction, because diffraction in physics is a limit for you to understand which kind of instrument of microscope should you use for your specific application. The second reason I introduced diffraction, because in the last part of my lecture today, I will change completely to another method. It's analytical method, allows you to detect crystals, to detect crystalline objects, biological, non biological, whatever. It's called X-ray diffraction. We will use X-ray to understand the crystalline structure of nature. So the diffraction limit, it's a limit in microscopy, but the diffraction is used to detect the distance of atoms in crystals. And using X-ray, you can do very, very easily whatever type of the object could be. So we can skip to the scanning electron microscope and the transmission electron, the main subject of this lecture. I'll introduce what is FEG. FEG is the type of source who, if you are working with electrons, somewhere you need to prepare to produce electrons. So FEG is this type of source. It's one of the type of source you can have to produce electrons. Well, I already talked about the story. Just a few things, probably I skipped, was well, the first SEM prototype was built by Dennis McMugler at the Cavendish lab in the 50s. At the same time, Professor Castin in France developed the first system to detect X-ray coming out after the interaction. So in the 50s, and the British group was focused on the construction of an instrument who could surpass the limit of the optical microscope. And the group in Cambridge developed the scanning microscope, the scanning electron microscope. And at the same time, the group, the Professor Castin in France, developed a system to detect the chemistry using electrons. So electron probe. So use electron to ionize, and after the ionization, I can detect the chemistry of the object. So the two different schools, they behaved in parallel, one for the chemistry, the other for the imaging. And now the results from these two schools was put together in a unique instrument can do both at the same time. The first SEM was sold to study fibers at the paper industry in Canada in 1955. And Dr. Danilatos in 1985 started to develop the first environmental SEM. So it's a quite new technique. And Professor Attini Donald at the Cavendish lab around in 2000 started to understand the interaction of electrons in high pressure atmosphere inside the SEM. So these are conventional scanning electron microscopes. Maybe you already found these instruments in many labs. These are conventional. I didn't put the E in front of the acronym. This is just conventional. You have a chamber in which you preserve your material. And you have a sort of detector. Remember, using a conventional SEM, your material, biological, whatever, must sustain vacuum and must be conductive. It's a limitation for some specimen, but in many, many other cases has a huge application. Metals, material science, whatever. Huge application of the classical. You can do morphology, you can do chemistry, but remember, the specimen must sustain vacuum and must be conductive. If the specimen cannot sustain vacuum, you can create what's called specimen preparation to fix, to block your specimen, not to change if you evacuate the chamber. So there are a huge type of techniques which allows you to fix your material, your biological material, but you change the material. Remember, if you have water, you remove the water and sustain water with another molecules to fix the shape. It's not anymore hydrated. It's fixed. You should know. You can observe the morphology, but you change the water molecule with other molecules that could keep the shape, the morphology fixed. And at the same time, if your material is not conductive, it's insulating, how can you do? As I said before, you can cover with a conductive layer. But in these two processes, you have to change your material. If you want to observe your biological material in the natural state with water without any treatment, you must use an environmental SEM. Okay? And the same work with transmission electron microscopy. Very, very, very few cases in the world are environmental transmission electron microscopy for very high resolution. But now we will deal with environmental scan because we have these instruments available. At the same time, I want to spend beautiful words also for the classical SEM. If you one day you work with metals or ceramics or whatever, you can use these instruments, which gives you all the information you need for. And we have two of these instruments with the environmental one. So in my lab, I have 3 scanning electron microscopes, 1 environmental and 2 classical, because most of the requests of metals and ceramics, I use the classical one. Why should I use the environmental when I don't need to use that for? I use the classical one. Only keep in mind the difference. Okay, electron-matter interaction. Start to go in some detail. With a microscope, you can get imaging, geomorphology, down to the nanoscale. And the imaging is point by point, a lateral variation of the intensity. And you can get a spectroscopy. If your microscope has the spatial detector to detect chemistry, you can do spectroscopy. So usually now, every type of instruments have these both facilities. You can measure the morphology, and you can have the information on the chemistry. So what happens? As I said before, some people can produce electrons. The electrons are focused on the surface. It's a yellow arrow here. And where the electron hits the surface, other electrons are produced or photons are produced. Okay, now I'm focusing on these 2 objects here, imaging and spectroscopy. So when an electron hits the surface, many different things could happen. And most of the systems are built to detect morphology and to detect chemistry. To detect the morphology, you have two types of detectors. One detector is called secondary electron detector. Is a detector which analyze, which collect all the secondary electrons produced. Remember the lecture before I said when an electron coming from the source is hitting the surface, you can produce other electrons, not the primary ones, but other. These are called secondary electrons. So there are specific engineering devices which collect these secondary electrons. How are defined these secondary electrons? Remember, this physics here. Secondary electrons are defined as electrons which escape the surface with an energy below 50 electron volt. Very, very small energy. I am using fast electron to hit the surface, but this device collects only the electron with very, very small energy, which comes out after the interaction. Since the energy is very low, these electrons are very, very low energy, the resolution, the volume from which they come from should be very small and close to the surface. Because if this is the surface of your body and you collect electrons with very, very low energy, if an electron with very, very low energy is produced in the middle of your sample, the electron has no, the force has no the energy to escape and to go out. Only those produced at the surface have the energy to escape, to go out. So for this reason, I collect only the electrons with very, very, very low energy, because automatically they come from the surface. They cannot come from inside. They don't have the force. They don't have the energy. They are produced also inside, a huge amount inside, but I collect only those which come from the surface. So with this engineering trick, collecting electrons which comes from the surface, but with very, very, very low energy, I have the chance to collect only those close to the surface. And if I use these electrons to create an image, which type of image would have at the end? An image of the surface. The best image of the surface I could have. I need to select these very, very, very low energy electrons. When you will work with the scanning electron microscope, you can select this type of detector, and the detector is called secondary electron detector. And now you know why you select this one, because you want to observe the surface. They come only from the surface. Look at this line here, high spatial resolution, 1 nanometer. With these electrons, you can get detail as small as 1 nanometer. Not microns, nanometers. Very, very, very small. It's a nanotechnology. You can detect the object down to the nanometer scale. And the contrast is morphological and topographical contrast. You have the shape of your object. No chemical information. You have the shape, the topography of your object. Remember, your object can change in chemistry. No. If you use these electrons, you can only have the topography. What are the other type of electrons I can get? Remember, I produce electrons, hit the specimen, secondary, but some of the would be reflected back. In English, back scattered, back reflected. So are electrons with energy much higher. The energy from the beam which are reflected back. So the energy of this electron is much higher. And with this electron, I have a contrast. The capability to be reflected depends on the atomic numbers. I send 10 electrons to an uranium atoms, all my 10 electrons come back. I send my 10 electrons to a lithium atom, maybe another one comes back. So the reflection depends on the atomic number. So if I use this signal, what could I get from the image? The different distribution of the atomic number. Where the signal is very high, I know that here, there should be an element with high atomic number. If the signal is very low, there is an element with a low atomic number. So the image is an image I call contrast by atomic number. Depends on the atomic number. So the secondary electrons gives you the morphology down to the nanoscale. The backscatter electrons gives you the distribution of the atomic number. Okay, this is just an image that shows you how these detectors are made and how they look like. This is the final part of the lens of the microscope. The electrons come from here, pass through this hole, and hit the sample, which should be here. And you have a different type of detector. This is secondary electron detector. And this is the backscattered electron detector, which gets electron which can back after reflection. The third signal, remember, you hit the surface, you have electrons, but you can have also photons. So the third signal are photons. In which range of wavelengths? In the wavelengths of X-rays. So if I detect X-rays from the surface, and I can do all of this I'm telling you now, you can do simultaneously. Not first the secondary, and no, you can do all simultaneously. Now the electronic is so fast that you can acquire all the signals simultaneously. With X-rays, with a specific type of X-rays we show you later, you can detect the element. So what is the difference between the backscattered electron and the X-rays? The backscattered tells you that you have a variation in atomic number, but don't tell you which is the atomic number. The contrast depends on the atomic number with the backscattered electron. You know that there is something change in the chemistry, but you don't know the chemistry. Unless you do calibration, very complicated calibration, you can do, but usually speaking, with the backscattered electron, you only have a map of variation in atomic number. The contrast, the gray, dark, white, depends on the atomic number, but you don't know which are. If you want to know the elements, you need to use the X-ray mapping. And look at this image on the right. This is just a cement particle put over a stub and just observing with secondary electron the particles. Oh, my cement is this particle. Well, there is those small particles around other particle. You see, with secondary electron, you detect the morphology, only the morphology. But if you want the chemistry, you need to switch on the X-ray detector. You switch on the X-ray detector, and at the same time, when you are acquiring the image of the morphology, the detector, if there are elements present, tells you which type of elements are you looking for and where these elements come from. So this is the signal of oxygen. And in this particle, I have the distribution of oxygen from this part here. This is a distribution of silicon. And from the particle, the silicon comes from this part. This aluminum, sulfur, calcium, whatever. You can select whatever. This is just an example from didactical point of view. Please, please.
Is it possible to calibrate the
Yes, you can calibrate, and you also
for example, the signals
the oxygen of oxygen is related to, I think, when you see the shape of where you have two information, not only the element you have detected, but how it's distributed. If you see it's related to the silicon, and probably it's oxidation of silicon.
I think a question. You also have not only this partial, but do you have also the quantitative?
Yes, yes.
I mean, the fact that the calcium is much more stronger, the signal means that there is more calcium.
Yeah, yeah.
Give you also quantitative.
This image, the image now I show you, is just an example to show the difference. But you can calibrate with standards. And if you use standards, we have standards, you can measure the chemistry down to fraction of % of sensitivity.
Now, my question is, in this example here, the fact that the calcium has a stronger signal means that there is more calcium than oxygen, for example?
Well, roughly speaking, yes. Roughly speaking. Because some elements could be ionized easily, and even if they are in a small amount, the signal seems higher. So for this reason, you need a standard, or at least a simulation. And when we do quantitative analysis inside the scanning electron microscope, we have standards, we calibrate the system with standards, and then we compare the experimental intensity to the standard acquired in the same condition. And in this case, I can tell you the chemistry down to a fraction of %.
So you need a standard for each of the elements that you are interested in.
Yeah. I have all the standards for all elements. And depend also on the matrix. You are working with biological material, we should prepare standards with a biological matrix. If you are looking calcium in carbonates, you should have standards of carbonates. If you have a calcium in silicates, you should have standards with calcium in silicates. And we have a lot of different standards as a function of the type of material. Not only the element, but the element with a specific environment, specific matrix. Because most of the interaction is also with the other atoms. But it's easy to do, it's not complicated. Just to acquire standards and calibrate your system. And remember, the same accelerating voltage, the same probe, the same condition. You cannot change the voltage of the microscope. If not, the intensity change because you have changed the intensity of the microscope. So when we do calibration with standards, and you know that mineralogy and people coming from geology ask quantitative analysis for their rocks, we need to check down to the fraction of percent, and everything are completely checked and stabilized in the same condition. When I told you before, remember in the Cambridge laboratory, Dennis McMullen was developing a scanning electron microscope in the 1950s. And at the same time, the French people, Professor Castain, was developing X-ray microanalysis. So the work of Professor Castain is only related to this. They use electrons to ionize, to have X-rays for chemical purpose. Professor Castain work. The work of the Cambridge group only for morphology and information on the structure of the material. Now both information can put together, and if you want quantification at high level, you need standard. If you want just a rough estimate, you can use systems which are called standardless methods. They compare the intensity with intensity stored inside the system, in the computer. It can give you roughly an estimation how much is it, but the error it's about 10%. Depends what do you need. People from the industry of minerals ask me for fraction of percent because they want to know exactly how much of these elements are present. Other people coming from other type of disciplines want just to know, oh, with this calcium, and it's a calcium carbonate, it's enough, but not quantification. Depends. You can have different type of software to do all the things you want. The best one, those which come from the work of Professor Castain in France, use standards, and with standards you can go down to fraction of percent, quantitatively. The merits of SEM. So as I said, it's a high spatial resolution method. You can get information, topographical information down to the nanometer scale. High magnification, high depth of field. This is another physical quantity. What is the depth of field? The depth of field is the height on which your sample remains in focus. So even if you have a complex topography, which valleys and the mountains in your object, you don't lose the focus. You don't lose the focus of your system. Always keep the information is in focus. Remember, when you work with an optical microscope, if you change the height of your specimen, or if your specimen has some valleys or mountains, some are in focus and others not. Because the depth of field of the optical microscope is very, very low. In the scanning electron microscope, the depth of field is very high. So even if you have mountains, valleys in your sample, always are in focus. So this is another advantage of the scanning electron microscope. And this I told you at the beginning, a classical SEM, the sample must be high vacuum tolerant and conductive, a classical SEM. When I talk about scanning, what does scanning mean? Why the name is a scanning microscope and not only a microscope? The optical microscope you use every day does not use any scanning at all. You have a parallel illumination, and your object lens takes in parallel all the X-ray, all the photons which comes out from the specimen. It's parallel illumination. But why should have to call this instrument scanning? Because the way in which the image is built in the scanning electron microscope is a way which uses a scanning beam. Where is it? Here. This is just to show you which type of signals are produced. And my electron beam, this, now is fixed in this point. It's always the same point. But in the scanning electron microscope, your electron beam is not fixed in one point. Moves. Starts from a point, then moves along a line, and then makes another line, another line, another line. So actually, from the electronic point of view, even if does not appear by working with the instrument, if you work with the instruments, the image seems continuous. But actually, from the electronic point of view, the image is acquired in this way. You know, I come from the mosaic of Ravenna. I come from this. So if you create an image using tessere, single tessere, you can create an image. The contrast in this mosaic is on the color. You use tessere with different colors to create an image. But you see, I put some lines. I don't know if you can see the lines, the black lines. Maybe you see the lines here. If you start with tessera, the tessera is a pixel. In electronics, even this screen here, or your phone, this is made in this way. Everything is made in this way. You don't see, but it's made in this way. So the mosaic tessera, the elements of image, in electronics is called pixel. It's the same thing. How you build a mosaic? Take one tessera, put another one beside, another side, another side, another side. So one tessera, one pixel, and another side, you create a line. And then you need to create another line. Mosaic tessera, a second line, and after certain amount of line, you have created an image. So the image of mosaic tessera is a digitalized image, a digital image, because it's made by tessera, or made by pixel. The screen of your tablet or your phone, whatever, is made by pixel. It's a silicon-based electronic pixel. Very, very small, you cannot see. You need a microscope to see the pixel, but it's made in the same system. And the image is built in the same way. But it's so fast that you cannot see. It seems a stationary image. But if you have a specific electronic device, oscilloscopes, you can see that even very, very fast, it's built in the same way. Start from one point, creates a line, another line, to have a frame. The scanning electron microscope works in this way. So the beam hits the specimen in one point, takes the information, then the beam moves one pixel aside, takes the information. another pixel aside, take the information. And then you have a line. And then you have a 1,000 line, 2,000 line, whatever line you want. You can select whatever you want. So the image is digitalized, is scanning, because your beam is scanning over the surface. And from every pixel takes the information. And then the software reconstructs the information. Secondary electrons, X-rays, whatever. Reconstruct point by point, pixel by pixel, the information. So an ordered sequence of pixels, according to parallel lines, provides you the image, one quantized image pixel. Please, yes.
Go back to the example that you showed. Graphic example.
Which one? With this?
No. Go back.
Tell me. This one?
No, it's been passed already.
Tell me which
Okay. Oh. This one. So if this image just give you a qualitative data, what you get from this different distribution here. I may say the oxygen more or less spread all over the cement. The aluminium is maybe more concentrated in one side, but there is other pixel that with the aluminium also in the southeast corner there, southwest corner. So what give you this? If there is no quantitative data there, what does it give? I can say if just qualitative, just put the point there all overlap.
But not all overlap.
All overlap.
Well. The first image on the top left, the cement. Yeah. Well, there is a particle of 20 microns by 10 microns. Oh, not only this particle. This particle has other smaller particle on the top.
Okay, let's talk about the
please. I did all the thing I can get from this observation. Okay, so the first is the morphology, the size of the bomb, whatever. The second one, okay, I put these elements. Oxygen is mainly related to this part. Sulfur,
so it's also quantitative.
no, not depending what you mean for quantitative. I cannot give you how much sulfur is there. I only say that. What do you mean for quantitative?
Percentage. I mean, okay, so I can say that sulfur is more concentrated in one point.
Yeah.
Because the signal is stronger.
Yeah.
So semi-quantitative.
Yeah.
So the particle is maybe random particle. Things kind of a chemical connection between aluminium and oxygen.
Yeah. But this is the first. The first fast information you can get is not quantitative. Is semi-quantitative. Gives you just an information of where are the elements distributed respect to the morphology.
You would know. Sure, it's
Well, you mean what would I do after this first image? Well, I want to understand exactly what is the chemistry of this object. So I extract this sample and I calibrate using standards for oxygen, aluminium, silicon, sulfur, and calcium, using standard with known concentration, and I compare the concentration, the signal coming from the standard, with the signal acquired.
Then a real quantitative data, you could say the amount of quantitative test of weight of mass.
Yeah, sure.
But if you don't do that, in this case, you have just a relative information.
What we call semi-quantitative information. You know that this particle is made of silicon, calcium, aluminum. If you do any analysis, you don't know anything about only the morphology. You know that this particle contains, and there are some not homogeneous distribution of elements along this particle, around this particle. They are not quantitative, semi-quantitative. More the signal is white, bright means more element should be. But I cannot say with this type of image here, how much is it exactly?
In terms of mass.
Internal. If you ask me, okay, we do the experiments again. I use standards and I calibrate the intensity with standards. And then I can give you information about the chemistry in a quantitative way.
Okay.
But another thing will be the spatial resolution of the chemistry, which is not the same of the morphology. So be careful, because I will show you later. The secondary electrons comes only from the surface. So the information you get, like the image here on the top left, with the information of only the surface. But the X-rays comes from inside. So the resolution, when you create an image using X-rays, is worst. It is not so good as those from the secondary electrons. For the physical principle of production of, I will show you later. So the X-rays comes from the bulk, from inside, but the morphology is only from the secondary electron. Okay, so the image is collected by pixel, as in mosaic. Now we have to define what is the contrast. What is the function contrast? The contrast is a physical quantity which tells you when you can discriminate two different objects as a function of a detected signal. I put just as generic as the signal. So if I have pixels, every pixel has a signal. I just show you here, this is a signal of one pixel, this is another one, the same signal, little bit less, much less, different steps, quantized steps of your signal. So the contrast is defined as the difference of the signal between two pixels respect to the first pixel. This is called delta Si over Si. And there is a criterion, the criterion for Rose, which means that to have to detect an information, the contrast should be at least the 5%. The difference in the intensity between two pixels should be at least the 5%. For every type of signal. This means that if the signal are less than the image appears the same color. Okay, so next step is the start to introduce other type of microscopes. We started with the classical SEM, also for historical means, and now we faced other type of information. So you have an incident beam, and with the incident beam in the scanning electron microscope, and also in the modification with the environmental one, you detect the information you can get from the top. So if you have the primary reflected, you have the backscattered electrons. if you have the secondary one for topographic information, and you can have the X-ray for the chemistry. But if your specimen would be thin enough, what could happen to your electrons you are using to create all these signals? Or putting the question in another way, if your specimen would be very, very thin, what would happen to your electrons? You always have this information, but in addition, you have that some electrons can pass through. But remember, it's not light. The specimen is interacting very hardly, very strongly with electron. So the specimen to be transmitted to be very, very, very thin. And see here, at least 100 nanometers. If not, the specimen is too thick, and don't have any transmission. So one day, if you will work with a transmission electron microscope, never say never. Maybe one day to have a maximum spatial resolution, even if biocrystallography, whatever. Remember, you need to prepare a thin, very thin specimen of your biological stuff, mineralogical stuff, whatever stuff, thin. And when I say thin, for electron should be less than 100 nanometers. If you prepare the specimen this way, you have the possibility to have electrons which are transmitted. And which kind of electron could be transmitted? What could happen of an electron when passed through? You can have three different types of signal. There are some electrons which are elastically scattered. They are reflected through, they're deflected through, so are elastically scattered. They don't lose energy. They're just with Bragg diffraction, crystallographic information. They could be transmitted by a little bit absorbed, point by point. And all these type of electrons gives you information on the microstructure or crystallography if you use diffraction, diffusion. If these elastical scattered electrons are diffracted by Bragg, you have crystallographic information. The other signal is this one, the transmitted one. And these are common signals in classical TEM. If you work with a TEM, you always have this one. The third one is anelastically scattered electrons. This brings you chemical information. So if an electron which comes from the source passes through, and passing through, while it's passing through, ionize an atom, extract an electron from the atom, ionize an atom, so heat has an energy, then heat an atom, extract an electron, ionize an atom, the primary electron lose energy, as not the energy as before. So the amount of energy he has lost is related to the ionization of the atom who has suffered the ionization by heating this electron. And this type of signal is called energy loss electrons. So the loss that the first electron has lost after the interaction. And this gives you a composition information. It's called through thickness compositional information. X-ray from the surface and energy loss through the sample. Most of the new analytical transmission electron microscope, TEM, have both type of signal. X-rays from the top and energy loss from the bottom, through the sample. And what is the difference? That the X-rays is a very high signal for high atomic number elements. So the probability to have X-rays is very high for atomic number with atomic number above 10, 11, with atomic number. But is more or less blind for low atomic number. So X-rays cannot see very low atomic number. On the contrary, energy loss electrons have a very, very high signal for low atomic number elements and not very good for very high atomic number elements. So you have both signal, you have the complete atomic table of them, but you need both. Okay, this is just a brief skip to the transmission. Now go back to the scanning electron microscope. So how is built a conventional scanning electron microscope? As I said, you have an electron gun which produces electrons. Everything you see is sealed inside this chamber, which is usually made of steel. This is called the column, and this is called gun, which is sealed to the specimen chamber, which usually is much bigger to allocate bigger sample. And then you have what is called the vacuum system. So everything is evacuated by this pumping system, both the specimen chamber and the column and the gun. Everything is sealed, only could be open when you put the sample inside, and then you need to close and to remake the vacuum inside all the microscope. You have your electrons, which are produced by a gun. The electrons are accelerated. They are focused by condenser lens, like in optics. And then the final lens is an objective lens, like in optics. You have your beam, which is focused on the specimen surface. Now the beam is in this slide is fixed, but you know this is a scanning microscope, which somewhere should be a system which move the beam over the surface. And you have scanning coils, which makes your beam moving, creating an image over the surface. You can decide the shape, the size, whatever, the time. And around your specimen, you have all the detector I showed you before. This is the main construction of a scanning electron microscope. What type of source do you have? Low cost, very easy to change, 10 euros per source, is a thermoelectric emission. So you have a filament made in tungsten. The filament is supplied by a current through an electronic system. For heating, for the passage of current, the filament heats up, and by heating, it produces electrons. And then there is a first lens, which is called the Van't lens, in which the electrons which are produced by this tungsten filament are focused in one point. Here, so the first image, first crossover of the electron which are produced here. Then this crossover, this point, is brought magnified, demagnified over the specimen surface. Advantage, very, very low cost. Disadvantage, not good spatial and energetic resolution. The electrons have not the same energy, so electrons have different energy, and this D0, the first crossover, is quite big. Even if you demagnify this on the surface, the resolution is not very good. But the system is a very, very low cost, depending on what you are looking for, what are your needs. If you need high resolution, if you need to have your probe down to few nanometers, or in some cases half a nanometer, you need to change the type of source. And the system we have in Bologna, we have this field emission gun source, which is completely different from this one. As I said, this cost 10 euros. This cost 20,000 euros. But with this type of source, you can have a probe down to 1 nanometer. You can have high resolution and with the same energy for electrons. So you see, the electrons comes from this crystal, and they are extracted not by heating the filament, but they are extracted just by applying a voltage in front of your filament. You apply a very, very high voltage, and the voltage is so high that the electrons from the crystal escape, because they are extracted away from the high field, the high electric field you have created. In this case, you can have a very, very, very small area from which they came from. And so the resolution is very, very high, down to few nanometers, with a very, very high intense. And the system we have this type of source. Very costly, but you have a much increase in resolution. So this is what happens with the field emission type of source. If you calculate the energy distribution of electrons if in a metal, you know that at zero Kelvin, all the electrons have boundary states which are inside the metal. But if you change a little bit the temperature, you have some amount of electrons which have energy, which can rise up the barrier to prevent electron escaping from the surface of solids. So if you have metals, if you have whatever type of solids, every type of solids does not produce electrons. Why? They not produce electrons. They are made of atoms. Every atom is made of electrons. Why electrons does not escape from any type of solids? Because to escape from the solid, they should pass a barrier. And for every type of material, they cannot pass the barrier. To produce field emission electron, you use a trick, a physical trick. If you apply a strong electric field, you change the shape of the barrier. Instead of an infinite barrier, like in the solids, the shape of the barrier, you see, as a function of the field. With a strong field, the barrier becomes very, very small. And the electrons, by a quantum effect, can pass through the barrier. So it's a quantum effect. The electron produced by field emission source is produced by a quantum effect. So the barrier is so small, the electrons can pass through from a quantum effect. In this case, you have a very, very high density current, lots of electrons. Look at the comparison between, and quantity of electrons which here, gun brightness 10 to minus 10 to 4. Field emission source 10 to 8, 10 to 7. So 10 to 4, much more electrons than in a conventional microscope. It's a very, very high brightness of the instruments. So you can have a small probe, few nanometer in size, with a huge amount of electrons. And this small source, you can move the source on the surface, and you have a lot of signals, even with a very, very, very small source. So in this case, you have increased the resolution down to the nanoscale with enough signal to create an image, but only with this type of instrument. What I was saying before, for a different type, remember, you don't only have to look at the type of signal for specific application, but you need also to understand from which volume do they come from. Even if you focus your electron in 1 nanometer probe here, what happens to your electrons inside the material? So every type of signal has a different spatial resolution. At the moment, forget about Auger electrons, which are particular type of electrons. I talked about secondary electron. They come from the surface, they come from here. Backscatter electrons, they come from the blue part. X-rays, for the chemistry, they come from this part here. So remember, the resolution is not the size of the probe. The resolution is the volume from which the signal comes from. And the three signals I told you, the most used every day, secondary, backscatter, and X-ray, have completely different spatial resolution. For bulk material, X-rays comes from micron, volumes of micron. But secondary electrons comes from nanometers. So coming back to this, remember, the topography has a resolution of nanometers. You can see objects of few nanometers. But the chemistry comes from inside the particle. Does not come from the surface. Comes also mostly from inside.
So if you have coated the sample by carbon, for example,
You
have the coating is carbon coating is interfering with the X-ray analysis, the elements.
yes, not much as gold, because you can coat with gold, which is much more conductive. But gold interacts very highly with X-rays, absorb a lot. The way to use carbon is the carbon is low Z elements. So the absorption is less, but you have an interaction. You have modified the surface and some absorption, you could have some absorption.
But you have an interaction only for the distribution of carbon or for the elements?
Some absorption you have also for other elements, depending on the energy of the X-ray which are produced. If the X-ray is very strong, they pass through without any problem. If the X-rays are very low energy, they could be absorbed by the carbon sources. For this reason, in the environmental SEM, we don't want any covering at all. So high source, higher number of electrons in small probes, and no hovering, no touching your cell phone, even keeping the water inside. So in the development of instruments, we thought about something in which you don't have anything to prepare to your sample. You can take whatever type you put inside. No modification. But the usual type of SEM are this one. Facciamo 5 minuti. Let's we have 5 minutes of break.
Okay. That's one. Quindi se io ho una mappa per ogni pixel riesco a ottenere dal software una percentuale atomica di atomi per ogni elemento che il software, se lo strumento riesce a rilevare. Ma senza calibrazione è una percentuale relativa, cioè
allora, ci sono...
cioè non posso dire esattamente quanta massa di calcio c'è, però posso dire se ho l'80% di calcio in un pixel, il software mi dà un 10% di alluminio.
Sì, ci sono abbiamo dei software che senza bisogno di standard, sono standardless, soltanto per le condizioni che tu fissi della colonna,
esatto.
Dal segnale che esce, tu ti dice
una percentuale di atomi
quanto
per ogni elemento. Quelli, diciamo, per avere io non voglio sapere quanta massa c'è di quell'elemento, mi interessa sapere la differenza relativa tra gli elementi, è valido.
Con un errore del 10%.
Non è piccolo.
Per standardless sono dei sistemi. Il tuo campione è anche rugoso?
No, è dispolished.
Perché se pulito, c'è lucidato, è buono. Se
No,
no,
l'abbiamo fatto il coating. Sì, il coating. Sì,
il polish. Allora, se
anche il coating abbiamo fatto.
Se lucidato, il carbonio sì, a meno che tu non abbia gli elementi leggeri che possono essere assorbiti, non so che elementi stai cercando.
Calcio, alluminio.
L'alluminio non tantissimo, il calcio sicuramente no.
Magnesio.
No, è come l'alluminio.
Cioè, no?
Cioè non viene tanto assorbito. Se il film di carbonio non è tanto spesso, le misure relative puoi farlo. Calcio sicuramente.
Cioè, a me interessa quando lui mi tira su questo pixel qua, che è, come dicevi tu, per la tessera, lui per ogni tessera mi dice che percentuale di ogni elemento c'è. Ed è una cosa relativa, cioè non voglio sapere in assoluto quanta massa c'è. Mi dà una differenza in termini percentuali che su 100.
Ricordi però che il segnale viene da farlo vedere
da sotto, vabbè. E allora?
Se tu, non so, sulla superficie hai visto un oggetto di, non so, più 100 nanometri, ti interessa lui?
No, mi interessa quello che c'è, come è fatto il materiale lì.
Il fascio arriva, prende lui, ma prende anche
va bene.
Il segnale che ti, capito?
Sì,
c'è anche quello che c'è sopra.
Va bene.
Lo faccio vedere dopo.
No, ma è importante che tu mi dica che se questa è la tessera, il pixel, lui mi dà una percentuale di atomi, okay, e le differenze relative tra gli atomi sono varie.
Se il campione è lucidato, usiamo un software di quelli con diciamo di standardless, abbastanza buono, 5-10%, io ti dico, tot silitio, tot alluminio, tot
percentuale. Su 100 mi dice c'è più calcio di alluminio. A me non mi interessa sapere esattamente, dammi la massa del dono, mi interessa.
Ma
Mi interessa la differenza.
non è leggero, non l'ossigeno. Non mi chiede l'ossigeno o il berilio o il boro,
L'ossigeno c'è, me lo dà, perché no?
che lì l'errore potrebbe essere. L'ossigeno ha degli errori enormi. Sotto, ma questioni fisiche, perché la radiazione è talmente debole che può essere assorbita e quello che misuri non è buono. Potresti beccare il segnale dell'ossigeno anche da altre parti.
Però i dati sono buoni, perché se io faccio il rapporto della tessera tra il numero tra la percentuale di ossigeno, di atomi di ossigeno e di atomi di calcio, un materiale che è carbonato di calcio, io mi aspetto che sia 3.
Sì.
Perché c'ho l'ossigeno. E mi viene esattamente 3.
Hai provato?
In ogni tessera.
Ah.
Una volta mi è venuto in 4, ma se faccio la media, diciamo, tra 1000, quanti sono 1000 per 600 tessere, la media è 3,0000. Cioè, quindi vuol dire che il dato è buono.
Ma l'avevi ricoperto quindi con un film sottilissimo di carbonio?
Sì, non lo so, l'ha fatto l'ha fatto noi, cioè non so che facciamo in casa, quindi è sempre lo stesso senso.
Perché il detector lì su quello, come se tu avessi avuto, hai trovato uno standard di carbonato?
Mi sto aspettando che mi mandino della ragonifettura, della calcifettura, voglio vedere.
Quello che sai che poi lo facciamo anche diffrattometricamente, quindi ti dico effettivamente che carbonato è, quello sai la composizione, ti metti nelle stesse condizioni e vedi lui la verità, però devi ricoprirlo uguale.
Uguale, no, comunque diciamo che con i dati che ho adesso, se io faccio ossigeno diviso percentuale di ossigeno diviso percentuale di calcio dentro ogni tessera, mi viene 3, che è esattamente quello che mi aspettavo. Il dato mi sembra abbastanza
buono, anche se non hai usato lo standard.
Ma perché a me è lo standard, per quello che dicevo, a me interessa sapere, cioè, se uso lo standard, perché io voglio sapere quanto in termini di massa c'è in quell'elemento, in quel materiale.
Per esempio, ti dico, noi sì, collega sedimentologo dei carbonati e mi chiede, mi fa l'analisi chimica precisa al decimo del %.
Sì, che cosa? Di quanta roba c'è di quelle?
Quelle sono proprietà, calcio, magnesio, tutti quelli che possono sostituire all'interno. Però la voglio quantitativa al decimo del %. Come fanno?
Gradi di massa.
Sì.
Se vuole sapere in peso, in massa, quanto ossigeno c'è di dentro.
Allora, mi dai gli standard dove tu mi già con altre tecniche hai detto quanto c'è di ogni elemento, il tuo campione te lo analizzo di fianco a quello.
Per poter fare un po'.
Quello è il metodo con gli standard, è il più preciso che c'è.
Invece sono felice, Giovanni, io ti do questo affare qua. Okay? Mi dici in termini relativi quali sono gli elementi più abbondanti rispetto agli altri?
Un errore di qualche 10%, 10%.
Guardo strano.
No, per dirti che l'errore è grande. Cioè non è come l'altro caso, posso arrivare a 0,1, 0,5. Lì, sai, le morfologie ti variano. Il campione l'hai metallizzato in grafico quanto spesso non lo sai.
Non lo so. Fare
Quanto era freddo? Quanto era grosso? Era molto omogeneo. Ah, beh, cioè, ma
era alto qualche millimetro.
dentro il carbonato può avere dei vacuoli,
Qualche sicuro.
quindi il fascio elettronico,
delle porosità,
il
può essere sia aperta che chiusa.
fascio
Ma
elettronico.
il campione è embedded in resina. Polish,
Quando colpisce qui, qua potrebbe beccare
3,
un vuoto,
potrebbe esserci della porosità appunto,
poi si sposta,
magari non lo becca,
quando becca qui non lo becca.
non c'è il vuoto, però succede.
Allora lì
C'è una variabilità, però dipende da
come fa, sì, da come è fatto, perché è poroso, non poroso, c'è della roba organica. Se te la becca, è quello che volevo dire.
matrice organica, il
Ragazzi, qui
24% è matrice organica.
entra dentro fino a 5 micron. Mentre i secondari ti vengono, gli altri entrano dentro 5 micron. Se tu dei pori lì sotto, lì magari c'è dei pori e il segnale ti viene bassissimo. Non c'è materiale.
Magari ci può essere anche la sostanza organica.
O sostanza organica che ti va a
La
alterare.
matrice organica, il 2%, 4% il peso.
Ma campione, quello lì che mi dà, l'hai sezionato nell'altra direzione, l'hai guardato al microscopio ottico per sapere.
Campionato trasversalmente rispetto alla classe.
Hai visto come è fatto qua?
Sì, se no, cioè, diciamo, è come tagliare un albero, tagliato così. Cioè, l'asse di crescita è questo e l'ho tagliato così.
Sì. E, no, per dire, tu sai cosa ci potrebbe essere nell'altra direzione. Il tuo campione l'hai sezionato come un altro. Tu nell'altra direzione, che gli elettroni
Sì, potrebbe esserci un poro.
L'hai guardato nell'altra direzione?
No,
lo puoi fare.
non lo so se lo posso fare. Però so che ci può essere carbonato di calcio, può essere...
Lo tagli per così e lo guardi qua. Perché se ci sono dei buchi del della sostanza organica, l'analisi è sicuro che ci sono 5 micro.
No, però devo dire, cioè, però questo mi vale. La variabilità ce l'ho su tutti i campioni di tutte le specie che voglio analizzare. E dipende dalla specie stessa.
Ci sono delle specie che fanno uno strato più continuo, non me ne intendo, magari di scemenze, uno strato più continuo nei primi 5 micron, e delle altre invece che è più poroso. Biologicamente, no.
E il software ti dà, quindi per ogni tessera ti dà la composizione in termini di elementi e ti dice anche questa tessera rispetto alle altre 1000, quelle che sono migliaia di tessere che ha fatto nella sua e in quali posizione è. Quindi si estrapolano anche i dati geografici.
Ricordati che sotto però fa così, quindi la tessera
E lì
è molto più piccola,
da dove va a prendere informazioni. Sì, ho capito.
tutti sposti, le due tessere, ma sotto praticamente quasi uguale di là. Poi magari alla quindicesima tessera va a campionare qualcosa che interessa. La misurazione dei secondari è 1000 volte più elevata. Nanometri confronto a micron.
Fanno un attimo.
Ma cosa c'è ancora un'ora fino all'1:30?
Chiaro, 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 chiaro.
Okay. Okay, we can continue. So, as I said before, this was the last slide. And remember, the resolution in the scanning using the secondary electron must not be confused with the analytical resolution. Always remember this one. If you have bulk, and for bulk, I mean samples with a thickness more than 5-10 microns, for me, 5-10 microns is bulk, you have this effect. If you want to avoid this effect, you must go to a transmission electron microscopy. But in the classical SEM or EZM, you have bulk samples. And with bulk samples, the region from which the secondary electrons comes from is very narrow, close to the surface. But the region from which comes the characteristic X-rays for the chemistry information comes from the bulk, comes from microns inside the specimen. Even if you are looking detail, very, very small 1 nanometer detail in the surface, the information comes from this area. Always keep in mind this. And this, for example, and this is a petrographic jet from a friend of mine, crystalline rock materials. So we have different type of crystals, different type of minerals on the surface, completely polished, whatever. You can have information from the surface, how the surface is made, but when you detect the X-rays, look what happens. X-rays goes and produce inside your crystal, and in escaping from the bulk to the surface, they can encounter other crystal, other mineral, and the final signal is related to this reduced resolution respect to the electron beam size. Always keep in mind. And also keep in mind that the X-rays which come from 5 micron in average can interact with other crystals aside, and the final information could be affected also by the side crystals of your object. You can simulate before doing the experimental part, and with Monte Carlo programs you can very easily simulate whatever type of material. Just to show you what you can do. You have, for example, your object with this green part. You can simulate a centered beam respect to the object, or you can simulate what happens if your beam is not perfectly aligned with the object. And you can have all the trajectory of electrons and the X-ray produced changing the position of the beam. This is for gold leaves 1 micron thick in glass matrix as a function of the interaction and the energy of your electron. You can have confinement of your information, or you can have scattering of your electron and producing X-ray which comes from the matrix because of the different physics of the system. And this is for silicon, sodium, calcium in this type of experiment. Another one, I reduced in the simulation the size of the gold leaves inside the matrix. So this is my small gold leaf 2 micron thick, and this is a centered beam. I focus the beam. Remember, the focusing is very, very precise, but what happens comes from a bigger volume. This is with a centered beam, and you see scattering of electrons and obviously X-ray produced by the scattering inside the material from outside. And this is not centered beam. You have a huge amount of trajectory from this part of the site. And so you have the production of other X-ray lines from the side of your material. This is another simulation. For example, just to suggest you try different energy of your electron. You are inside a scanning electron microscope. You can change the energy of your electron. If you have your material, which is this simulation is a fiber radius of about 700 nanometers, and if you focus your beam in this position, as a function of the energy of your beam, look how much is localized the information. With 25 kilovolts, your electrons pass through your object, which is almost 1 micron inside, pass through, and you have generation of other things from all the other part. If you change the energy to 5 kilovolts, you have the localization of your information only from your glass fiber. So take care and think about the localization information, and you can change the energy of your beam. Not a fixed amount. You can change during your observation. I will skip to, okay. So we have faced the limits of conventional SEM. And remember, the surface must be conductive and the sample must be tolerant to the high vacuum. Just to show you what happens in a classical lab. These are dust particles on the top of a specimen. And you see this black region around the particles. This arise because the particle charge up, so they become always more negative. And if the particles are negative, are not conductive, the electrons which comes from the source are not capable anymore to hit the side of the specimen to the particle. So they are deflected away. So you lose the information because of the charging effect. This is a nylon fiber without any coating. You see all these lines is a charging effect because it is charging. It's not, and this is what happens to the observation of a pure alumina sphere after the time. After the time, the alumina gets electron from the source, is not conductive. And look at the image aside. The image is completely deformed because the trajectory of your electrons, which come from the source, are completely deflected by the field of the alumina, or the electric field generated by the alumina. So the alumina generate an electric field, and the electron which come from the source are deflected by the electric field because your material is not conductive. This is the means to use a real environmental scanning electron microscope. So in the scanning electron microscope, conventional, we are limited to this level of vacuum. In the SEM, we can go up to 50 torr. Usually 4.6, 5 torr is a common value of pressure you can work with, but the system can go up to 50 torr. And to exploit this, we need to go back and see the thermodynamic equilibrium curve of pure water. So this is the vapor pressure from and the state of the function of temperature of water and the change from liquid to vapor pressure. So at this this value of temperature and pressure, we can keep the water in the liquid state. And we can arrange the chamber of our instrument to work in this field here. Just changing the temperature or changing the pressure. We can keep the water in the liquid state inside the instrument. Only in the region of the specimen, not in all the other part of the instrument. Only where it's needed, which is only the surface of the material. The samples does not necessarily have to be vacuum tolerant, and the sample surface does not require any electrical conduction or treatment. You can do observation without any preparation and keep the water in the liquid state. Samples can be conductors, semiconductors, insulator, whatever type. And also this extends to dynamic in situ experiments. Since you don't have to prepare in any way your material, you can do whatever you want. You can make mechanical test, tensile test, compression test, whatever, because your sample is not prepared in any way. Can sustain whatever type of interaction. Hydration, dehydration, you can change the temperature, you can change the pressure, you can change the whatever. You can treat your material inside the chamber. How the system is built, this must be known because to avoid problem during those preservation. The same column, the same and chamber is geometrically similar to a classical scanning electron microscope. The difference is only allows me to do this only in the vacuum system and the way the vacuum is applied to the microscope. I use this picture in which with different color, I depicted different zones which are at different pressure. So the upper part, we have the gun, the field emission gun. The field emission gun must work in very, very, very vacuum condition, very, very low vacuum to have the field effect. So here in the green part, you need to have 10 to minus 8, 10 to minus 9 torr. But in the chamber, the red part, you can have 0.1 up to 20, 40 torr. Look at how many order of magnitude of difference between from where you generate the electrons and where you have your material to be observed. So the region in which you need to have this high value of pressure is only this part here. Only this red small part. It's not important to be behind or look, but this small part here in which you have the specimen must be at this very, very high pressure. So how can you prevent water molecules or whatever type of gas molecules coming from this area, which is a high pressure, to this area, which is a very, 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 very low pressure? This is a gradient of pressure of 10 order of magnitude. So you have a flux of molecules which should start, move from the high pressure region to the low pressure region. So the idea was only from engineering point of view. The system is built with many, many different subchambers. Soon after the red one, you have an orange one chamber with a vacuum which is a little bit better than this one order of magnitude better. And after the orange one, you have the yellow one. And the yellow one is a little bit better than the orange one by one order of magnitude. And then you have all the other chambers up to the final one, which is the region in which you have the gun. This is called the differential pumping system, limited by apertures. What is an aperture? An aperture is a diaphragm with the size of 1 micron or fraction of microns. So half a micron is huge, enormously huge to pass the electrons. But half a micron is very, very small to move water molecules from one chamber to the other. It's called some sort of vacuum impedance unit. So the hole is very, very small for water molecules. And the difference in pumping is very small because the gradient is small, because you have created a lot of different chambers, and every chamber is separated by micron size diaphragm. So the gradient is very low, and the hole is very small to prevent molecules to move from one part to the other one. Very, very tricky and complex from the engineering point of view. You need all this stuff here, and all this stuff here is a different pumping system. Every chamber has its own pumping system and it's controlled and compared to each other to keep the difference very, very small, to avoid molecules to move. And in this way, you don't have any loss of electrons. The electrons can be produced here. They move through the column, through this very, very small aperture, down to the sample, and the sample is very, very close to the final aperture. So the electrons which pass through the final part at very high pressure have to pass a very, very, very small path. So they don't lose energy, don't lose much information during this part. This is the building, the construction of a typical field emission, high vacuum and low vacuum environmental SEM. You can change the pressure, you can change the temperature. The only thing that try to keep very close the distance between the sample and the final aperture of your material. This is magnification of the last part of the instrument. This is the way in which you have your material, which can contain water. And look at this magnification. All these are different specific chamber with different vacuum level between each to the other one in a few millimeters in size. So the gradient is very, very, very small in the final part. The system can work in many different ways. You work in the classical high vacuum mode, yes, you can do that. You can work in low vacuum, you can work in low vacuum. You can change the pressure, you can change the pressure. So you have a huge variety to working condition in the SEM mode. The other thing is you don't need to cover your material if it's insulating. Why? You can do this in this type of instruments because there is an effect which automatically neutralizes the charge at the surface of your material. This is called ionized gas amplification signal or detector. Your electron hit the sample and produce secondary electron, like in the other instrument. But these electrons create a charge in the position. How this charge could be neutralized if the material is not insulating? Is insulating. So this is just a scheme. This is a primary beam. Hits the specimen, create a charge here. Electrons produced are acquired to create the information. During the escape of the secondary electrons, electrons are not in vacuum. Electrons, remember, you have high pressure here. So the electrons, secondary electrons, now encounter molecules. The system is not in high vacuum. The system is high pressure, this part. So the secondary electrons produced by the primary beam are accelerated toward this biased anode. During their paths, they ionized the molecules, the water molecules you have in the chamber. Remember, you have a high pressure inside the chamber. You have molecules. So the secondary electrons ionize, and statistically, after one ionization, you have a production of more than one electron. Remember, ionization means to extract one electron from the orbital, but one secondary electron can produce more than one ionization. So if you multiply, you have what is called a gas amplification. You have an amplification of electrons. At the end, at this level here of the positive bias, you have an amplification due to the gas, due to the natural gas you have inside the chamber. So we are using the water molecule as an amplifier. So the secondary electrons produced are amplified by the water molecules, by this effect, without any need of specific preparation or whatever. every secondary electron produces a huge amount of electrons due to the molecules which are close to the surface, automatically, without any need. You need only to collect the final number of electrons by this amide. And what happens to the molecules? Remember, the secondary electron have ionized the molecules, and then ionize the molecules, and then ionize the molecules. All the molecules have become positively charged because they have been ionized. So you have a huge amount of molecules which are positive. And the electron beam is hitting the surface. So automatically, the water molecules or the gas molecules, which are ionized, go to the surface, take away the electrons, and become neutralized dynamically. Please ask if there's something to explain. Please ask without any. This is automatically system automatically create a zero charge surface, but this always working this principle. So secondary electron creates positive molecules, and at the same time amplification, the signal. The positive molecules are positive, go to the surface which is negative, and the surface not more negative, and the molecules became again neutral as a function of time. Always these things, all these mechanisms as a function of time. You always have a neutral molecules because of this effect. And at the same time, you have amplification. So you don't need any amplification, external amplification, and the surface is always kept to zero potential. And your molecules always become neutral without need to changing the molecules. It's only engineeristic, but it's the fact you are using to have the surface of your material, biological one, full of water, no problem. Insulating, no problem. You can observe without any modification, change, whatever, due to vapor or due to electric charge. You can observe your material. So this is the principle of working of the classical environmental microscope. There are many other effects, but probably I don't have much time. The electrons which are produced inside the material can suffer different scattering events. You don't have any coating. Remember, in this the environmental one, you don't need to coat. So you are looking at the surface, completely pure surface. This is the gibbsite crystal observed with a backscattered electron. But if you use a gaseous secondary electrons, which are electrons produced by different part of the crystal, you have a contrast. You see the difference. This is a very high energy electron. So this is electrons with very, very low energy. Electrons with very, very low energy show you that this gibbsite crystal was grow in different steps, and you see the different steps of growth of the crystal using this type of signal, because they come from a different region, a different source of a spatial region respect to the mineral. Okay, well, the resolution, this is just a resolution test. You can go down to 2 nanometer in resolution, even in water vapor presence over the sample. 5 torr and 10 torr, you have a resolution of 5 nanometer. Probably just I want to skip to the other one. As I said before, since you don't have to prepare in any way your specimen, you don't have to coat, you can do a lot of in situ dynamic experiments. We can discuss later about this. You can apply mechanical force, you can cool, you can heat, and see what happens to the material. X-ray microanalysis. Okay, this last part. When an incident electron hits an atom, one of the possibility is that the incident electron removes an electron belonging to the orbital of the atom. This is called ionization by incident electrons. So my incident electrons has removed an electron from an orbital of my atom. Can the atom remain in the ionized state? No. What are the probability to come to the ground state again? That look at the image. An electron of an orbital close to the first orbital jump in to replace this empty position. In this jump, there is a release of energy, and this release of energy is in form of a photon, of an X-ray. And the X-ray has the energy of the difference of energy of the two levels. But even if this electron jump here, this electron leaves a hole here. So the probability of another electrons from another orbital to jump here. And this second jump, there is a production of another X-rays. So after one ionization of an in-core level, you have a huge amount of jump of electrons to these holes created by ionization, which produce a huge amount of different type of lines. But each lines, energy of each lines of every X-ray is specific of the quantum jump. And every atom of the periodic table, every atom has his specific energy jumping step. So if you measure the energy of the X-ray, automatically you have the information of the chemistry, not only from one line, but all the line associated to all the jump. This man studied all the possibility jumps you can have after ionization. And this is called the Sigban notation. Every X-ray has a frequency, and every frequency is associated through the Planck constant to the jump in energy. So all jump in energy create an X-ray. You just measure the X-ray energy, and you know which element or how many elements what are inside the sample. Very, very easily. So not only the morphology, not only the backscattered electron, but also the chemical information from this part of instrumentation. I skip this. There are programs which from the red arrow is the direction of the analysis, experiments. You have a sample and you measure the sample. The black one is the direction of the quantitative analysis of your material. So you have the total emitted intensity You are observing your material, your probe is fixed in one point, you are collecting the spectral. Total intensity recorded. If you know the fluorescence of a specific material, which are inside, it's called the F parameter, you can derive in the way back, the black arrow, the primary emitted intensity. What does it mean? Remember, the electrons goes inside micron and are ionizing micron inside. And X-rays are produced in this small volume inside. These X-rays are escaping from inside to outside. But what an X-ray can produce from moving from inside to outside can escape easily or can interact with the matter which is around. Remember, they are produced inside and they need to escape. During their path to escape, they found material and then can ionize material, is ionization due to X-rays. This is called F, secondary fluorescence. So you need to know this effect because from the total intensity you have recorded, you need to remove the fluorescence effect. So the ionization due to this, to the effect which is not derived. After you have removed the secondary fluorescence, you have got the primary emitted intensity, the real intensity which are produced inside. Then you need to know another effect, which is called absorption. This intensity produced down, 5 microns down, and try to escape. All these X-rays can escape or something could be absorbed. As a function of the energy, some could be absorbed, other less absorbed, different way. So you need to know the absorption of X-rays inside the material. Factor A, absorption. Then you correct for the absorption, and you have the primary generated intensity. And from the primary generated intensity, you have the generation, the atomic number, what you are looking for. Summarizing, there are programs which correct what you are recording with your computer, the total emitted intensity. There are corrections which are called ZAF, ZAF, which correct for secondary absorption and generation.
The software that we have,
Yeah.
they do the correction.
Yeah, you can do the correction.
So
So
you have the concentration.
at the end, you have the concentration. But remember, you have your material, which is produce ionization. You have all this effect, and you record this. Now you have to come back to have the real concentration of your material using this procedure. Well, there are a lot of programs for quantitation, using standards, using the background. I don't want to focus now on this part here. There are a lot of programs for quantify the chemistry using standards and using simulation. Last part, because I think I have only to show you. Okay. This. I would like to change to another method. Is always a scanning method, and it's called a scanning probe. As I said before at the beginning, we can have another type of instruments, which is a scanning microscope, but does not use electrons. It uses probes, not electron probes, but other type of probes. This type of instruments is called scanning probe microscope. And I would like to show you some application and how does it work. Okay. The image is recorded and acquired with the scanning method. So the microscope takes the name scanning because you get an image using the scanning principle. But look how does it work. Imagine to have a very, very small pyramidal or cone facing downstairs towards the surface of your specimen. This is the probe. It's a nanometer, mechanical nanometer size probe, which is facing the surface of your material. The probe can be moved X and Y, and point by point, you can acquire an image. Is a scanning principle. Now the question is, but that type of probe, what can measure? What type of information you can get with this type of microscope, of instruments? A lot of different type of information you can get. First of all, I would like to show you that the probe, which face the surface, is fixed, is glued to a cantilever. Cantilever is a very, very, very small lever, 200 micron long, 5 micron thick, and 10 micron wide. Very, very small lever. And your probe is fixed to this lever, facing downstairs. See here? So you have a lever, your sensor, your probe, and your surface here. And then you can move, you can rise up, you can lower down your probe respect to the surface. If you have a attractive coupling, if you have attractive force, what do you expect? The cantilever deflected toward the sample. If you have a repulsive force, you expect a deflection of the cantilever outwards the sample. How can I measure the deflection of the cantilever toward the sample, so outward the sample? How can I measure? It is measured in this way. We have a laser. The laser is reflected to the back of the cantilever, and the image of the laser is made in focus to a 4-quadrant photodetector. So the laser produces a laser spot, the laser spot is reflected, and the image of the spot is completely in the middle of 4 photodetector. You know what is a photodetector? Photodetector is a detector which gives you a signal as a function of how many photons are arriving on it. And if the image of the laser is just in the middle, how in the same way I show you here, perfectly in the middle, the amount of photons which arrive in the quadrant A is equal to the amount of photons in the quadrant B. is equal to the amount of photons arriving in quadrant C and the quadrant D. Because I have 4, and the image is perfectly in the middle. So each quadrant takes the same amount of light at equilibrium, with no force acting on the tip. Now, if there is an attraction, the cantilever go down, and the image goes down. So the signal of C plus D becomes higher respect to A and B. And very easily, I can measure an attractive force. Opposite, if I have a reflection, repulsion, A plus B is measured, then C plus D. And if I have a torsion, A plus C is different respect to B plus D. In this way, I can measure at the nanoscale attraction, reflection, and torsion. So if my tip, my finger, feel the surface, and the surface has different friction coefficient, you have torsion, different torsion as a function of friction. You can measure the friction properties at the nanoscale, but you can measure also the attraction or the repulsion. You can measure a lot of other physical quantities in environmental, in ambient condition, in atmosphere, without, and also in liquid cell. These methods work perfectly in liquid inside a Petri dish. So if you have cells, if you have tissues, if you have biological material, you can set your tip inside the water dish, and your tip can feel the membrane of your cell, and you can image your cell perfectly in liquid, in biological condition of your material. If the membranes becomes harder, you can feel that the membrane becomes harder. If the membrane becomes softer, you can feel the membrane becomes soft. You can measure topographical and mechanical property of your material, biological material, in really living condition. You can, I don't know, you are biologist, you can feed your cells and you see if the feeding change the condition of the membrane, or you can attach at the top of the tip a molecule, and you can measure if this molecule is attached in a specific position of the membrane. You can localize the interaction. So you can create your microscopy, you can create your experiment, use this type of microscope. It's not an electron microscope, it's a scanning probe microscope, works in atmosphere, in liquid, whatever. You can think of different experiments. It's very, very small. This is the screen of a computer. This is the chamber. Here you have to put your specimen, 1 centimeter wide. This is the head in which you have integrated everything, the tip, the torsion, the measure, whatever. So it's called the atomic force or scanning probe microscopy. And I would like to describe this system to make clear the difference with the scanning electron microscope. Both are scanning, both can resolve at the nanoscale, but the information you can have are completely different, and the environment of the sample is a little bit different. Here you can work in atmosphere and in liquid. In the scanning electron microscope, you can remember, you can work up to 40 torr. Not perfect environmental or a classical standard atmosphere. As a function of the distance between your tip and your material, you can have different type of force. If you are quite far, you can measure fluid film damping. If there's a film, a water film, or whatever fluid, which can dampen the oscillation of your cantilever. Or you can measure electrostatic force, attractive or repulsive. You can measure surface tension of fluids. You can measure van der Waals forces. And you can measure Coulombian forces, which are repulsive. And this is the surface of your material. So as a function of the distance, different type of force will act and will interact with your probe. And you can work at specific type of force. You can want to measure and monitor the van der Waals forces. You can set at the distance in which the van der Waals force are acting. You want to measure the Coulombian force. You set the tip at the distance in which you have Coulombian force. You can set the type of force you want to measure. Just to show you some example, you can go down to atomic resolution. This is the surface of a muscovite. Muscovite is a phyllosilicate on which on the surface you have the distribution of oxygen plane, and you can measure, you see, the hexagons of the crystal down to angstrom resolution. If you dissolve with acidic attack, with chlorhydric acid attack for 4 hours, the surface, you can measure the steps you have created after acid attack of the mineral. You can change the type of mineral. Is another phyllosilicate, phlogopite, and again you can see and you can measure down to the atomic scale defects on the surface. You can have different type of probes, but probably it's better to show some examples. Well, this is just a curiosity. This is a classical commercial pyramidal tip. You see on the top, I created another tip. Just putting the cantilever inside an electron microscope. And inside the electron microscope, you have contamination. I used the contamination, the carbon contamination, to create a super tip. A tip much more thinner respect to the commercial one. So the commercial one was this one, and using the carbon inside the electron microscope, I created this even more sharp tip to increase the resolution. You can functionalize your tip physically, then change the tip geometry. You can functionalize chemically. You can set specific bonding chemical groups on the top of the tip. And you can biological functionalize the tip. Ligand, receptor, functionality, molecule, cell, and intermolecular force. Antibody, antigen, antibody. You can create the interaction at the top, and you can monitor at the surface where you have the interaction. These are examples of physical. You can attach a sphere, you can attach a carbon nanotube, you can create a very, very sharp, as in the case before, on the top. How the system works? You can work in contact mode, intermittent contact mode, and not contact mode. In constant force, you can rise up and lower down your material to keep the deflection of the cantilever constant. In this way, since the deflection is constant, the force applied to the surface is always the same. Look at the simulation, look at the laser. The cantilever never bends, keeps the same bending. So you are working at a constant force. You only have to rise up or lower down your specimen, because some biological materials are very, very soft. And if you apply a too strong force, you damage the biological material. So you can keep the force width very low and ask to the system, don't change the force. Rise up and lower down the specimen, keep the very low force to your material. In constant height, the back of the cantilever is kept at a constant height, but the force changes. Look what happens. Look at the laser. It's deflected in different points during the scanning. This could be used for high resolution in inorganic material, hard inorganic material, not biological one. You have a risk to damage the cells in the skin. Okay, how the chamber is made? The chamber is like this one. You see this glass, transparent glass, in which you have your cantilever. You have a substrate, and you have your cells and molecules. Every are fed by fluid, water, whatever, and your cantilever moves inside the liquid, inside the sun. So you can observe living object with this instrument, with this environmental cell. What time is it? 1:30, okay. Just to show you, okay. There are minerals that after cleavage can present at the surface positive or negative zones. These regions are confined in a few nanometers. So in classical cleavage of the chloride, this mineral called chloride, you can have simultaneously at the surface both positive or negative parts. This is a topography of chloride, and with the system, you can measure the potential, and this is the distribution of the electrostatic potential after cleavage of your chloride. You see, not only edge, not only steps, but you can correlate the steps with the potential. Remember, one is positive and the other is negative. So using chloride, I have a surface in which at the nanoscale, I have positive and negative, I mean from charge point of view, steps on the surface. I used this surface to condense biological material. Since biological material has charge, I thought that in the positive or negative part of chloride, I can condense DNA, RNA, nucleotides, or amino acids, or cells. This is just filaments of DNA absorbed on muscovite, on biotite, and different type of mineral has a different affinity for condensation of DNA. This is talc and this is brucite. In brucite, you have also entangling of the DNA filaments. But the chloride presents two layers at the same time. And this is a measure of the absorption of the DNA as a function of time in chloride. Chloride tends to agglomerate only on the positive part. This is black with the white areas after 5 minutes, 14 minutes, 21, and 30, all the liquid was completely removed from DNA. DNA went only on the positive part. But look at what we observed between two positive layers. We have some DNA filaments. We are in stretched condition. So the potential of the mineral attached the DNA in a stretched condition. I don't know if you can see the filaments here of DNA. The 3 filaments of DNA between the positive. And then I used the tip to cut one filament. So this filament here, I cut with the nano scissor, the filament, and the filament, you see, disappeared and reappeared here, interacting with a part of the surface. We used the tip to modify the morphology of this filament. I think could be enough. And well, I thank you for. If you have any question, please feel free to ask. Thank you. To saltare un po'.
No, one question could be how they can have access to the instrument.
Insomma, ci vorrebbero 10 ore forse. Si può studiare le interazioni. Vabbè, basta. Ok.
Grazie Giovanni. A question could be if a student want to access, for example, the ADS or another instrument that you have that are running at our department. How are accessible this instrument?
Yeah, sure. Perfectly. For the ESM, environmental scanning electron microscope, usually the professor or the project group ask me to make the observation, and we arrange an appointment we discuss what is the type of experiment, what type of observation we are looking for. We discuss together, and then we can give access to the instrument. The same thing for the atomic force.
But we are the also.
Yeah.
Okay, so I guess it's time for a break.
Something.
Let's go. I'll see you later. We'll see you later.
Okay.
Okay.